Okay, this. Okay, hand it in, please, and the lob in.
Did you do the questions?
You do have to do the questions too, yeah?
Oh, okay. Then I guess that's good.
Can you just turn on the, thank you.
Do you need the board also?
No, not yet. I don't think yeah, I'll be using it later, but thanks. I'm okay now. Okay. So, make sure we're recording. Yeah, we're recording. Okay. Let's just go over for the test, the torque test, equilibrium test. It's not just torque, it's also translational equilibrium test on Thursday. So it's equilibrium, right? So that means translational equilibrium which means chandelier type problems, no beam. Translational equilibrium and rotational equilibrium. Okay, so as far as breakdown as far as structure, it's about 6 to 8 multiple choice, and it's just a mixture of both types. So 6 to 8 multiple choice. Again, same idea with that. You'll have to show all work, 2 marks each. Two, 3 written. Okay, with more focus on rotational. So 2 rotational equilibrium. With, okay, 2 parts to it. I think they both have 2 parts. Well, expect 2 parts for both. With 2 parts. Okay, so I would go over all the different types we did. all the different rotational problems we did. So whether it be this type, you're responsible, remember, for always going over all the content. I'm trying to help you out by narrowing it down a bit, but that's my version of a straight line. So that type, what we did yesterday, the diving board type. Okay, that type here, which is a platform, almost like a bridge. That type, solving for one of the unknown forces. Here you'd solve for this force here. You'd probably in this one solve for F1 and F2. Same thing here, F1 and F2. Okay, start off by using the condition for rotational equilibrium. And then part two would be using the condition for translational equilibrium. Let's go back here. What does that mean? This is the condition for translational. X and Y. This is the condition for rotational. Okay, so with each of these problems here, and again, I'll add more in a second here, but with each of these problems here, you start off with the condition for rotational. Then you use one of these or both of them to solve for one of the other forces. With this, getting back to this first type of rotational problem, remember you'll have, in this, you'll have an FV and an FH, which you may have to solve for as well. That would be your part two. Okay, we also did problems involving beams at an angle, not level with the ground, so be ready for those. How it's set up, there's different types of problems, right? But there'll be like a mass here somewhere, maybe a mass here. Weight of the beam acting down this way. You'll be given the angle here. Okay, you have to know how to deal with the geometry. There'll be another force somewhere, could be at the very end. That's your force. Solve for the force. Solve for the forces at the pivot as well. I'm not going to get too fancy with pivots in all of these problems. Unless stipulated, there may be one on the multiple choice, but unless stipulated, the pivot's going to be on the far end, the left side. Okay, remember you're always responsible for everything we covered. I'm just trying to give you the main points, the main things we covered. I think that's it as far as different types. Maybe one more, but that's it, basically. Anything else? As far as there's one, like I said, there's 3 written questions. The 2 harder questions are rotational, which will start off by using this. And then if there's a second part to it, you'll end up using both of these or one of these. Condition for translational. And then the other, I said there's 3 written. The third written will be translational. One translates strictly like a chandelier problem. Something that looks like that. One translational problem. So what will that look like? It generally looks like this. Jeez, yeah. Why is it not? Oh, okay. Maybe it's this. Yeah. It generally looks like this. Okay. Now, what it asks for you could change. There's a variety. There's different varieties of this. You could have F1. You could have FG. So check, and maybe the question is find F2. One of those forces will be unknown, F1 and F2 or FG. So which one I will ask the question on, that's the variation, right? In this diagram, I just said what's F2. Could be what's FG. Question could be what's FG or what's F1. Or what's F1 and F2 given FG. There's variations on this. This problem, remember, the steps basically are the same. You're going to have two equations in general. I can't go over every specific. You have two equations. Okay. One will involve the sum of the forces in the x being equal to 0, and the other one will be the sum of the forces in the y equal to 0. And again, this is in general. You'll rearrange question number 1, and you'll, whatever the variation, whatever the rearranged form is, you'll plug into equation 2. No, like I think in the multiple choice, there's a variety. I can't tell you what the ratio is, but I'm telling you in the written, there's 2 rotational and 1 translational. Yeah. Pardon me, like this triangle?
Within each diagram, there's a triangle.
Are you talking about this one? I'm just going to give you the basics as far as what to expect. Yeah. Go over the review that I mean, you're going to hand in the review assignment tomorrow. I'll give you full solutions to that. I didn't obviously in that handout tell you to do every problem. I would do them all. You're going to have full solutions to all of them. Okay. So go over that. Make sure everyone's got to hand that in tomorrow. Is that clear in the back? Hand it in on time so I can get the review to the rest of the class. If it's not in on time, I'm going to force you to do it so I can give it to the class at the end of the lesson.
It's all the multiple choice, right?
I said about 6 to 8 multiple choice and 3 written.
Oh, no, like for the homework.
Oh, for the homework.
All the multiple.
Yeah, I just gave you mostly multiple choice. I think there was 2 written, right? Yeah. I also have another review sheet I'll give you tomorrow, but I don't have full solutions. I just have answers, right? And again, a reminder with the assignment, you've got the answers at the back. I did that on purpose, right? I'm marking the solution. I want to see you know how to do the work. Okay. So, I mean, judging from what I've seen, you should do well. You guys are, don't let it go to your head. You're one of the best classes I've had, so. It's true. So far. So far. You're very good. Keep it up. That's all I wanted to say. Okay. So today we're going to start a new unit. Certainly I can have a little time at the end to go over more equilibrium problems. Like I can give you a little time to work on the end of today, the assignment, 15, 20 minutes, and then you can ask me personal questions. You can come up here. I can do it on the board. I can do it here. But I've got to move ahead. So this is a new unit. Circular motion. Circular. Circular motion. Okay. We're going to deal specifically with uniform circular motion. It's going to be uniform. There's accelerated forms of this. We don't deal with uniform means, in our case, constant speed. What does it simply mean? What did I just say in simple words? It just means anything that moves in a circular path, anything that moves in a circle. Looking at a side profile, this is either a side profile or a drone view of some sort of object moving in a circular path. The object's moving like this in a clockwise direction. At what? At constant speed. That's what we're going to deal with. It's easier to deal with constant speed. There's lots of things that approximate this. The wheel on a car, if the car is traveling at constant speed, the wheel will move with a constant speed. Planets around the sun, we can approximate constant speed. The moon around the earth, any moon, but we're going to zero in on the moon around the earth, constant speed and a roughly circular path. I mean, if we were going to get into more detail, it's elliptical, but we can approximate it with the circle. A Ferris wheel. This could be, you've heard of a Ferris wheel, right? Ferris wheel at an amusement park. They move at constant speeds. When they get going up to their top speed, they start moving at constant speed, right? Lots of rides at P&E. They're circular rides and they spin you in a circle. They're moving after they get to their top speed, they're moving at a constant speed. So all of these arguments work for that. Cars going over a hill. The top of the hill approximates a semicircle. So if you're moving over that at a constant speed, we can deal with that type of motion. Moving around a turn. So moving around a curve. If you took like a drone view, if you took a drone up at a racetrack and you looked at some of these cars, we'd be looking at just the top half of the circle because they would move in a semicircle around a turn. As long as we're moving with a constant speed, the description that we're going to give pertains to that. So a lot of different examples where we can use this description. You're done already. Perfect. Thank you. Okay, I need your lab. Need your lab? All labs handed in, right?
Yeah.
You got 1 minute. I don't get the lab, it's late. Yes, that's being marks off.
How much is the lab for?
I want to squeeze in another lab, but I'm concerned about time, so they're going to be about 2%, 2.5% each, right there, please. Yeah. Okay. Constant speed. So things to be aware of when we're moving at constant speed. First of all, we need to know, obviously it's simple, but we need to know where the center is because I'm going to talk about that a lot. Okay, and I'm going to use this word a lot. Centripetal. What does that mean? Center seeking. Pointing always, in other words, center seeking means always pointed towards the center. Okay, so how does that pertain to this type of let's say this is a drone's eye view of a car going around a circular track. I mean, they do exist. So let's say that's happening with the car. Let's take different points. Let's look at the point at the very top of this circle. In order for him to keep moving in a circular path, there has to be a force pointed towards the center. I'm going to call that FC. Now, it is a net force. The C stands for centripetal, center-seeking force. Center-seeking force. Yes, it's in newtons, obviously. And it is a net force. It is a special type of net force. It is a net force, which means it causes an acceleration. It causes an acceleration. What type of an acceleration? It's going to be called or labeled AC. AC stands for centripetal acceleration. Okay. Now these are vectors. So and it is a net force. So I said earlier in the course that the acceleration will always be in the same direction as the net force. So if we go back to this diagram, I'm just going to color it a slightly different color. That's the AC. That little purple arrow, that's your centripetal acceleration. It's in the same direction. What direction? Always pointed towards the circle. So let's draw it at this point. I'm looking at this point now. Which way is the centripetal force? Again, towards the center of the circle. This is not cooperating with me, but that should be more pointed towards the center. But anyways, that's the centripetal force. Centripetal acceleration, same direction. At the bottom, the very bottom here, same idea. That's your AC, always pointed towards the center. That's what causes the car to move in a circle. At each point, it will move in a circular path. What does an object tend to do unless a net force acts on it? I want you to answer. You can write it down. You can put up your hand later if you want. Write it down. What does an object tend to do unless a net force, assuming it's moving, it's not at rest, it is moving. What does an object tend to do unless a net force acts on it? Say again? So if the forces are balanced, what type of motion does it tend to continue with? Yeah, the same motion, which is constant velocity, constant velocity, right? So that's the key. So an object, unless there's a net force, an object, if it's moving, it will continue to move at constant velocity. Okay, unless there's a net force. Okay, so let's go back. How does that refer to or pertain to this diagram? Well, at each point, let's draw the velocity. At the top, I'll call position 1. Remember, the object's moving this way. At the top, I want to draw a different color because otherwise it gets confusing. At the top, that's the velocity. I'll call it V1. That's the direction the car wants to move. That's why you would, if you don't have good enough tires, resulting in enough friction, that's why if you're moving around a turn and there's a cliff directly in front of you, but you want to make that turn, you'll go off the cliff if there's not enough friction. You'll move in this direction here. Rather than what? Rather than moving in the red path along the curve. So the green arrow is the direction that you want to move in naturally. And you will move in unless what? Unless there's a net force preventing you from doing that, keeping you in the turn. At each point, we'll call this 2 here. At point 2, this was velocity 1. This is velocity. Actually, I got to draw it. I want to make sure you get something really important here. That is, they are equal length. They are equal length. Okay? But different direction. So at position 2, you keep moving this way here. Unless what? Unless a net force prevents you from doing that. You don't move in a straight line at each point. You move in a curve because of the centripetal force. Okay, and then similarly here, I'll call this position 3 here. Draw the green arrows equal length as much as possible. I know mine are not perfect, but as much as possible. Draw them to be equal length. Equal length means same speed. Same speed. The car doesn't change its speed. It's just changing its direction. No, off phone. Jill. Off. Is that notes?
Yeah, no, I'm checking. That's inertia, right?
The tendency to move at a constant velocity is inertia,
Okay.
unless a net force acts on it. Yeah.
I was just,
That's fine. I mean, I just avoid using the phone, please. Okay. So it's important you understand in each of these cases, 1, 2, and 3, the car is still, it's a car moving around a circular path. This is a drone view. The car is still moving at constant speed. Yeah. So you want to make a note of that. V1 and V2 are still same magnitude, different direction. Why did I say that the velocity, I did mention earlier, okay, constant speed does not mean constant velocity. Okay, so there's two aspects of velocity. There's the magnitude and direction. So if either one of those changes, the velocity is changing. So in this case, the velocity is changing because the direction changes. You go from here, you pointed towards the east, now you're pointing towards the south. Direction is changing. But the speed doesn't change. Magnitude stays the same. That's the type of motion we deal with. Constant speed. So you want to make a note of that. V1 and V2, V3, same magnitude. At any point, I only drew 3, right? I mean, I could draw a 4th here, but I won't, whatever. You got it. I think you get that. So you can apply this not just to a car moving around a circle. You can apply it to the Ferris wheel, to a moon going around the Earth, to a satellite going around the Earth, as long as it's moving at constant speed. So V1, V2, V3 have the same magnitude. What is the magnitude in this case? Speed. Same speed, but different directions. Why different directions? Because the force is changing the direction. There's always a force at each point. The force is going to act at each point. What, in the case of the car, what is that force? It's the friction in the tires. The specific centripetal force changes depending on the scenario. For the car, friction here is the same as the friction here in magnitude. Different direction, but same magnitude of friction. Keeping the car moving in a circle as opposed to moving this direction or moving this direction or moving this direction. Why doesn't it move this direction again? Because of a net force. If you all of a sudden had tires that you hit a slippery surface at any point, then it would move in the direction of the green line. Yeah.
so all the forces that we say are the same, but all the
Yeah, that's the next point I was going to make. Okay. The other point that I was going to make, and you just hinted at it, is that yes, the directions of each of these purple arrows are different, right? This one's pointed down, this one's pointed to the left, this one's pointed up. They're all, however, pointed towards the center. That's the first point. I mentioned that earlier. But look at the size of the arrows. I tried to draw them equal in size. So the force is the same in magnitude. similar to the velocity. Similar to the velocity that it's the same magnitude but different direction. Okay. So the force FC, I'll put it in purple. FC, and it's a vector, so I indicated that, has different directions at each point. Okay, yes, it's always pointed towards the center, but you can see that the top, the FC is pointed down. Position 2, it's pointed to the left. Position 3, it's pointed up. So it has different directions at each point, but the same magnitude. Constant magnitude. Same thing applies to this centripetal acceleration. Okay, same thing for AC. Same thing for AC. Constant magnitude, yes?
Unless there's an F net.
Oh, unless there's Fnet, an object. Sorry, my printing actually is usually pretty good, but not on this thing. I don't know why, but unless there's an Fnet, an object, this is an. Yeah, I want to read that. An object continues to move at constant velocity. So that just has to do with what I said earlier. See how I drew these, these dashed lines here? That's the direction it would move. If there, unless a net force acts on it, it would keep moving in that direction. The car would keep moving in that direction, but there is a net force caused by the friction and the turning of the wheels. So it doesn't move in that direction. It moves in the circular red path. Okay, I only drew 3 points. Remember, there's a multiplicity. There are many points on the circle I could have drawn, right? I only chose 3. It applies to many different points, whatever point you choose. So, I mean, I could choose a point up here. Let's choose this point. Okay, that's the direction. What am I drawing here, by the way? I am drawing, you could call this V4. This is position 4. When I draw the velocity is the tangent to the circle. I'm assuming you know what a tangent is, right? Yeah, it just touches the circle at one point. And it's perpendicular. The velocity is, in all cases, perpendicular to the radius. Perpendicular to the force, which is perpendicular. Same thing as saying it's perpendicular to the radius of the circle. If I were to draw the radius here, I'll draw it a different color, whatever. That's the radius. For a circle, the tangent is perpendicular. So the velocity is always perpendicular to the radius at that point. And it has a real physical meaning. That's the direction that you would move. You would move in this direction. If you hit a slippery path, you no longer have a grip. You keep moving in that direction of the dashed line, green line. But if there's enough friction, if you hit pavement, then you're going to move in the red circular path. Okay? So we're going to look at now equations that connect. We know this. We know, at this point, we know the centripetal force is equal to ma. where A is the centripetal acceleration. We know that. What we're interested in is how is it connected to, how does it relate to velocity? I don't want to put that, but I won't even put equal yet. That's confusing. How is it related to velocity? That's what we're interested in. That's what we're going to look at next. Show you a video on that. This guy does a really good job. And plus, I think you'll be amazed. Look at this. This guy is writing on a piece of glass. He's the inventor of this. What?
So let's say you have to read an incredibly long email from your boss that you have to finish before the big meeting starts in 10 minutes. Or you're cramming for an
Oh, I didn't. I can use the speakers of the projector. Didn't know that. Okay. Okay, so he's actually, this is a professor out of, I think it's South Cal, so Southern California, University of SoCal. He's really good. He had actually invented this. It's going to look kind of strange to you, but it looks like he's writing on a window. He is actually, but he reverses, there's a trick to it. And it's well lit so that the writing appears pretty clearly. I like the way it's presented. He does a good job. He's going to derive the formula that, if we get back to this, he's going to show us how we can relate the centripetal force and acceleration to the speed. Yep.
Slightly off topic with the mirror. He doesn't write backwards. But he writes
No, I think when if you were a class, he does use a mirror. In our case, what he's doing is he's filming it head on and then he's reversing it in post. But there's more to it than that. It's not just a piece of glass because it has to be properly lit.
Yeah.
So, and I don't know. I think it's just a great way of presenting. So you can watch a lot of his videos into college. He does great explanations. So let's watch this. We're going to still take notes on this because we need to know you need to know the basic steps on how to derive these equations. So yeah, take some notes. I'll be stopping it and pointing out the main facts that he goes over. Okay. Yeah.
Hello, class. Professor Anderson here. Let's talk about uniform circular motion. And let's start this discussion by asking you guys a question. Are you accelerating right now? Sitting there in your chairs, rapt attention, probably glued to your chairs because of gravity, not because of that.
Yeah. And don't answer me verbally. Write it down. What do you think? Are you accelerating right now? Are you accelerating right now? On the surface of the earth. Well, you might not hold to this if you're a flat earther, but let's say you believe in it, as most of us do, that the earth is a sphere. If you're a flat earther, you don't have to answer this. It's fine. Huh. I got a friend who just reveals he denies that they landed on the moon. That's another discussion. We'll talk later. We'll break. Yeah, he denies the lunar landing. I've given up arguing. I used to get into this, not worse than me. Okay. So, yes or no?
Are you accelerating right now? Yeah, I see some heads nodding. Why? If you haven't thought, raise your hand. Yeah.
Because we're orbiting the sun.
Because you're orbiting the sun. Okay, the Earth is of course orbiting the sun, and therefore we are moving in a circle. But we're also spinning on our axis, right? The Earth is spinning, and so we're moving in a circle here as we are trapped on this Earth. And I would say that yeah, we are definitely accelerating, because if you are moving in a circle, uniform or non-uniform, you are in fact accelerating. Okay? But does it feel like you're accelerating right now? Not really. It feels like we're stuck on this big ball of dust, right? And we're not moving up or down. down, it doesn't really feel like we're accelerating. And that's because the Earth is pretty big. And the Earth is pretty big. And for its size, it's not spinning around that fast. Right? We're actually moving about 1,000 miles per hour right now. But for the size of the Earth, that's not that fast. When you get on a small merry-go-round and you spin around on the merry-go-round, you definitely feel that acceleration. All right, so let's talk about uniform circular motion. Okay, uniform circular motion is just this. Something is moving in a circle of radius r, and it's moving at a speed v. Uniform means constant speed. And later we will learn about non-uniform circular motion, which just means that the speed changes as you go around. But for now, let's just consider uniform circular motion, which is constant speed. Okay, that's what our picture looks like. We just said that we think we are accelerating. And we can probably convince ourselves pretty quickly that that is true, because acceleration is delta v over delta t. And delta v is the change in velocity. It's velocity of vector or a scalar. A vector. So if you have a delta v that's non-zero, that could be due to change in speed.
Okay, that's what we're used to. You're used to referring to an acceleration when an object changes its speed, when it speeds up or slows down. That's what we've been dealing with up till now. But there's two ways of changing your velocity. First one being change in speed.
Magnitude of velocity, or it could be change in direction. Okay. When you're driving down the road and you turn your wheel to the left, you feel that acceleration because you're changing the direction of your car. You're not changing the speed of your car, especially if you don't hit the brakes, you're just changing the direction.
Okay, so going around a corner. As long as you don't hit the brakes, you're not changing your speed, you're changing your direction. So that's an acceleration as well. Call that a centripetal acceleration. You're moving in a circular path.
So, how does this lead to an acceleration? How does changing the direction lead to an acceleration? Well, the way we're going to visualize it is the following. Here is a section of our circle. Here is a radius vector, r. And we're going to identify this angle that you traverse as delta theta.
Okay, so he's going to derive the equation that relates the acceleration to the speed. You don't need to know every step. You need to be aware of the basics. I would write this down, make some notes on it. What you need to be able to do is apply the equation at the end. But it's important you know the basics of the derivation. Derivation meaning how you get to the final answer, the steps, basic steps. He's going to use geometry. The problem is it's not your fault. Your geometry is not as strong as it used to be. They've taken a large component out of the curriculum, but I think you can follow along with most of the steps.
And we'll move in this direction. Okay. Your velocity is always tangential to the circle in uniform circular motion. So the initial velocity is there, the final velocity is there. We have clearly changed directions for our velocity.
Okay, so notice the way he drew it, the velocities are perpendicular to the radius. That's what a tangent is on a circle. A tangent is perpendicular, and that's what a velocity is. It's a tangent. Tangents are always perpendicular to the radii. Now, notice another thing. He wrote down a VI and VF. They're different velocities, not different speeds. Because the direction of this VF is pointed slightly down. It's different, a different direction than the VI. There is a change in direction. Related to this angle here, this small little angle.
And so that is going to lead to an acceleration. Okay, so let's take a look at this picture in a little more detail. Right, where did I start? I started at a position there, R initial. I ended at a position there, R final. Okay, vectors for position, they always define relative to some origin. We'll make the origin the center of the circle. The difference between those two is, of course, right there. Okay. So, what about the velocity vectors? Well, it looks like the velocity vector VI is up and to the right. But VF is down and to the right. And if I do the difference of those two, remember you can do your tip-to-tail approach by flipping the sign of one of them. But you can probably convince yourself pretty quickly.
I'll show you later how he got that, but for now, that is the change in velocity. That's the difference between VF and VI. That's VF minus VI. That's what you get. I'll show you visually how to get that later, but just accept it for now.
I was going up, I've changed to going down, and so the delta V has to be pointing down.
Okay, remember something about these triangles. This, even though they're different directions, the radii are the same magnitude. So the distance or the length of the RI is the same as the length of the RF. The length of VI, since it's constant speed, the length of VI is the same as the length of VF.
All right, but these are just magnitudes now. The radius of the circle doesn't change. That side is just delta R. If we are in uniform motion, the speed doesn't change. That side of the triangle is just delta V. Both of these are making an angle delta theta. All right, this is the way we define it. How do you see this? Well, this is always a right angle. And that's always a right angle. So if I add 90 degrees to VI and I add 90 degrees to VF, they both are going to traverse the same delta theta.
So he's just saying this angle here is the same as this angle here. The angle here is the same as the angle here.
Okay, let's go back to our acceleration. We said that acceleration was delta V over delta T, but if I look at these pictures now, those triangles are similar. And if they are similar triangles, then I can write the following. Delta V over V is exactly the same as delta R over R. And now I can solve this for delta V. I get delta V.
Okay, so this part you'd know if you knew your geometry better. Since these two sides are equal, and these two sides are equal, and the angle in between those sides are the same, this ratio must follow, because they're what's called similar triangles.
V times delta R over R. I just multiplied across by V. And now let's plug that into A. A, the magnitude of A, we said was delta V over delta T. And here's my delta V. And so I can plug that in. I get V over R times delta R over delta T, which I carried in from there. But delta over delta t, that's just how far you've gone in some amount of time, which is again just your speed. Delta r over delta t is just v.
Delta R over delta T is just your speed. How far you've gone in time.
What we now call centripetal acceleration. And it is A equals v squared over r.
That's your final
We
equation.
typically put a little subscript on it, either C or R. I like to use R for radial. Some people use C for centripetal.
Okay, so we're going to use C for centripetal. You can use R for radial, but it's the same thing. That's your equation. For a constant speed, an object moving at constant speed in a circle. The equation is the acceleration is equal to v squared over r, where r is the radius of the circle. And v is the speed of the object. Yep.
I'm assuming AR means they're the same thing.
Yep. You're gonna see AC more often than anything else. Yeah.
But what this means is anytime you're moving in a circle, you have a centripetal acceleration towards the center of the circle, which has this magnitude, v squared over r. Okay. That's how fast you are accelerating towards the center of the circle. So let's go back to our original question, which was, are you accelerating right now?
Yes. Because you're moving in a circular path as the Earth rotates at a constant speed. Okay. So let's do that. Let's go over. So this is your equation. Did it just stop recording? No. Stop recording. That's your centripetal acceleration. And your centripetal force is just multiply that by the mass. Okay. Okay, just one more derivation here. For this, I'm going to let's go back to the circle. Okay, so given a circle, I want to derive one more equation here. Given a circle of radius r, okay, we're going to calculate another expression for the speed. Speed, because it's constant speed, remember the equation for constant speed is just d over t. We can use this equation over and over again. Constant speed. What is this d when we're talking about the circle? For a circle, that d is the circumference. It's the distance around the circle once, circumference. Okay, what is this time? You're talking about going around the circle. Let's say you start here and you move all the way around and you come back to the same point. What's the time? That's the time to go around once. Okay, so this is the time. If that's the circumference, this is the time to go around once. And return to your starting position. Okay, what is this called? This is called, the proper name for that is period. And the symbol that we use is, this is the confusing part. People confuse it with tension. That's why I like using FT instead of T. The symbol we use for period is big uppercase T. So the equation becomes circumference for the speed, for constant speed. The speed is given by the circumference divided by the period. Okay, obviously the circumference is in meters and the period is in seconds. So you get the proper units for speed, meters per second. What is the circumference in terms of the radius? Don't tell me, write it down. Yes, it's equal to C over big T, but what is the circumference in terms of the radius? Write down what you can remember. You need to memorize some of these equations, simple equations, circumference of a circle, area of a circle. You need to know that. Two times pi times r. That's the equation of the speed in terms of the radius and period. So proper units, yeah. Radius is meters, period is seconds. Yes, proper unit. Okay. On a side note, just remember, we don't use this very often, but on a side note, the diameter is twice the radius. Oh. D is equal to 2r. D is equal to 2r. Diameter is twice the radius. D is the diameter. Okay, we mostly use radius. Okay, so back to this equation. This is our equation for speed, constant speed around a circle. Equation for constant speed around the circle. That's how we started the equation. Constant speed around a circle. We started with this equation, which is applicable to constant speed. And then I narrowed it down to the case of a circle. Yeah.
Does T equal time?
T is the time to go around once. It's a very special time. It's not just any time. It's the time to go start at the top or any position. Start at the top and go back to the top. Time to do that is big T. It's called period. And it repeats. The period is the same. Every time you go around and come back to your starting point, it's the same amount of time. if you're moving at constant speed. Yeah. Okay, now let's go back to this here. That's our equation for centripetal acceleration. Just rewrite it to remind ourselves. So this is the first equation. Equation number 1 is here. Now I'm going to derive a second equation for the centripetal acceleration in terms of the radius and period. You plug in this here. You plug in this for V. So you get 2 pi r over t, square it, divided by the, don't forget the radius in the denominator, divided by the radius in the denominator. Now, squaring anything in brackets means square each factor. Square the 2. Square the pi. Square the radius inside the brackets. Square the period. And don't forget, there's a radius in the denominator as well. Okay, don't tell me, write it down, simplify it. Simplify it in terms of less terms and then simplifying the square. Turn it into one number if you can. Two squared is 4. Pi squared, you can keep it as is. It's a constant on your calculator. Okay, one of the r's here will be canceled out by the r in the denominator. So you get simply r over t squared. What is that? That's just the second equation. This is the first equation. This is the second equation. Which one do you use? Well, it depends on what you're given. Use equation 2 when you're given the radius and period. When you're given the radius and period, use equation 2. Either one gives you the centripetal acceleration. What's the period? The time to go around once. Time to start here, go back around to your starting point. That's the period. In seconds, not minutes, not years. You have to convert it to seconds. This is a common mistake, in seconds. Okay, and in meters. You get the correct units. Yeah, on top you'd get meters. On the bottom you'd get seconds squared. Which is the unit for what? Yeah.
Put the 2 like outside of the red box.
That's just telling you, I labeled it question or equation 2. It's not part of the equation. That's why I put a box around it. Equation 2 as opposed to equation 1. Okay, it follows. If the question is find the centripetal acceleration, you use those equations. If the question is find the centripetal force, then just multiply by mass. You've got 2 equations. You've got that one. And you got this one. Put the line underneath the whole. Yeah. pi squared over t squared. Two equations. Which one to use? Depends. If you're given the radius and period, you use the second one. Wait, this is the second one. This is the first one. Okay, a couple of things, side notes. You can think of centripetal acceleration as how it's related to how quickly you're changing your direction. It's related to that. The faster you change your direction, the greater the acceleration. Think of it as that. That's probably as physical as you're going to get with it. One more point. We don't use this that often, but you should be aware of it. Period, again, is time to go around once, return to your starting position. Another way of defining it, a more kind of objective way to define it, is the time for one cycle. Time for one cycle. You'll hear this a lot. What's a cycle? Repeating pattern. A cycle is a repeating pattern. What's a circle? If you go around once and then another time, you repeated the pattern. Repeating pattern. That's what a cycle is. Does it have to be a circle? Well, with what we're doing it is, but you can extend this to anything that's a repeating pattern. So something like a ticker that moves back and forth, that's one cycle. Back and forward, back, that's another cycle. Forward, back, any pattern that's repeatable is a cycle. So a wave going up and down. You're sitting there on the shore and you're watching these waves. Oh, it goes up and oh my gosh, it's coming towards me, but I'm so tired because I'm listening to it. I can't. It's going up and down. That's one cycle. Up and down. Second cycle. Up and down. Third cycle. Any repeating pattern is a cycle. A car wheel going around once, that's a pattern. Going around twice, that's the second pattern. It's a pattern repeating itself. Tapping on something. As long as it's a repeating tap at a constant rate, every time the time in between those taps is a period. What's the repeating pattern? Tapping. Okay? My sound wave, because it's a wave, it has a repeating pattern. You can actually, I could draw it for you, but then you'd laugh at my drawing. But it's a repeating pattern. It's actually a compression wave that's reaching your eardrum. So there's a period to the sound wave. Okay, one more thing here before you get your break here. This is it's the inverse of the period. Mathematically, this is called frequency. You hear that a lot. Frequency is related to period. Frequency is just, mathematically, frequency is the inverse. It's just 1 over the period. I've been putting, so, and the period, this is got units of seconds. So frequency has unit of frequency is 1 over seconds. 1 over seconds. Or hertz. That's what a hertz is. A hertz is the inverse of a second. 1 over second. So when you hear the expression megahertz, frequency, a radio wave, in the frequency of megahertz, it's just 1 over seconds. Mega meaning millions of them. Mega meaning million hertz. A million 1 over seconds. Okay? Sometimes this is abbreviated HZ. There you go. You're done for now. We'll come back to it. We'll continue later. Everyone got that? What you want to go over? I'm just going to end the recording here, and I'll come back to it. Okay. You got a question? Stop recording. Stop recording.